a really nice vintage signal tracer with a couple more tricks up its sleeve. Will it still work? Let's find out together. Hello everyone, welcome back to the channel. I've got here a really nice piece of test equipment. It's a vintage signal tracer from the 1960s. According to the Radio Museum, it's from 1966. I don't know how accurate that is, but yeah, it will be from the 60s. It's a Vegaty signal tracer, model S.T.4. The S.T. will probably stand for a signal tracer. The 4 is maybe fourth version of the signal tracer. And it's a bit more than just only a signal tracer, but we'll go into more details soon. Yeah, it's made in Belgium, which is also quite nice. Vegaty was I don't think they still exist. It was a rather small Belgian company producing mainly test equipment. And they also made this signal tracer. Yeah, it really dates from the time that we still could make our devices ourselves instead of having everything manufactured in China. But this, yeah, was a Belgian company made in Belgium, so I thought it might be worth to feature it here on the channel. I picked this up recently, rather cheap. I don't know if it still works. I haven't tried it yet. So we'll have to figure out if it still works, maybe do some repairs on it, let's say a light restoration. Main thing is get it working so that I can use it as a test equipment, maybe swap some capacitors, these kind of things. A major point is also the probe is missing, so I don't have a probe, so we'll need to make a probe ourselves. Don't think that'll be difficult, but that's also something that we need to do. Yeah, for the rest, I think it looks quite nice. I found on Radio Museum also a picture of one with a wooden case, so I guess there were different types of cases available. This is just a metal case. I don't know if that means something in terms of production time frame or anything, if this is older than with the wooden, or you can just choose which type of case you wanted. I also do have the service manual, or it's more the user manual, and it's quite extensive. See, I printed this on both sides of the page, and I think it's 6 pages, so 12 in total. It's in 2 languages, French and Dutch, and we have the schematic here, so we can go over that. And then we have a very extensive mode of operation and all the things that you can do with the signal tracer. So let's have a quick look at the schematic first, just very high level. We'll come back to it later when we need some specifics. But as you see, it uses a couple of tubes. We have an EF86 over here, an ECL82 over there, an EZ80 for the rectification over here, an EM80 Magic Eye, or an EM83, and then an ECC82, that's this one over here. It's not marked on the schematic. But what this basically is an amplifier circuit, but you have the speaker over here and the input over there. So you just go through these stages of tubes to the speaker, an EM80 to get the signal strength, and EZ80 to do the rectification. See, we have the transformer here, and then an ECC82 for some other things. We'll get back to that one later. Yeah, so this is more or less a classical signal tracer schematic, but since this was a device which was really aimed at the, let's say, a bit more serious amateur market, what they did is they added, that's quite funny actually, they added lots of functionalities or things that you could also do with a circuit like this, so that they could add cheaply into the device without adding too much components. See, so that's what they explain here. Okay, it's in French and in Dutch, but let me quickly translate. So the signal tracer allows you to quickly and accurately detect every error, I don't know, but hey, you have to sell your devices, right? In an AM or FM radio, television receiver, or an HF, a high frequency or low frequency amplifier, or other electronical devices. Okay. And then they say the use is not limited to repair, because it also can be used to discover badly designed circuits and contribute to improving every type of circuit, blah, blah, blah. And then they hear, that's really interesting, this part is what they say is, apart from many other usabilities of this device, we also highlight the use as a VTVM, so a vacuum tube voltmeter, a 2-watt low frequency, so audio amplifier, an interphone, etc. So this is quite interesting. They added a lot of connections here and some very basic components to the circuit, and then they go into high detail to explain you what are all the things that you can do with this device, and not just using it as a signal tracer, but also lots of other different applications, like see here, detecting a hum, detecting distortion, see here, and then they give example circuits of radios. For example, this is the printing was not that fantastic because it's not printed in the correct order, but they do give you some explanations on how you can test circuits in a radio. So see here you have an amplifier circuit, and there you all the points where you can test and what you should measure over there. This is an IF circuit, where you also all the test points and what you can measure or how you can test these types of circuits. Here they go into further detail on how you need to use it in television sets, or how you can even use it in other motors of any household equipment, or to find faults in a car's circuit, these kind of things. How you can use it as a voltmeter, a vacuum tube voltmeter. So yeah, but the first thing that they do in the manual, where is now the page again, is they go over the dials and the connections that we have here on the signal tracer itself. So here we have an RC connections, and these, apparently they say you can use these to check continuity. It's basically a continuity test, so you can use it to check if a resistor is still fine. You can use it to check potentiometers and to check leakage on capacitors. See here we have the RC connectivity. One of the pins is of one of the input is connected to ground. The other one goes through a neon tube. That's this guy over here. And then the other connection, it goes through the neon tube, and it's basically directly connected to the rectified DC high voltage. So if you connect a resistor between here, or if you just connect them together, your neon tube will light, so you know that there is continuity. If you put a capacitor here they also explain what you should see when you put a capacitor. They say you will see a short flash because when the capacitor is charging, and that flash should go out or should dim when the capacitor is still good. You cannot use it for electrolytics because they have a very small leakage current in itself, and it will light the neon anyway. But this is a very rudimentary capacity leakage tester basically. So that's already nice. Then we have the input, so that's this one over here. This is where you would normally connect the probe. Now, as I said, I don't have a probe. It was not included with the device, and as you see here on the schematic, we have a drawing of the test probe, the demodulated probe. And you see that there is a diode, a germanium diode, and a capacitor and a resistor inside to do demodulation of an AM signal, for example. So we're gonna have to build something like this. That shouldn't be a problem. It looks quite simple. Then the next pin, that's this socket over here. That's a connection of 6 volts AC and 250 volts DC. So what it basically does is it exposes the filament winding of the tubes, and it also exposes the B plus of more or less 250 volts DC, so that you can use it as for testing purposes. So it's basically a you can use the signal tracer then as a power supply, a non-variable fixed power supply, and the characteristics are 6 volts 1 amp AC and 250 volts 40 milliamps DC. And what is funny is they say that if you remove the ECL82, you get 6 volts 2 amp AC and 250 volts 70 milliamp DC. But obviously you cannot use the signal tracer then for other purposes. Then it's just a power supply. But yeah, see, it's just, yeah, because they added a socket here and exposed these voltages, you can use it as a power supply. Quite funny. Then here we have a connection for a speaker, an external speaker, and depending on how you plug it in, you can deactivate or the internal speaker or leave it in circuit. Here you have the on-off switch. Then this one over here with the square wave icon, that is an input signal for a square wave. So I don't really completely understand their reasoning here. They say, well, you can supply a 1 kilohertz square wave on this bus. And because it's very rich in harmonics, the signal can be heard on a very extended frequency range, from the low frequency until the medium frequency range, and it can give you a lot of advantages when doing repairs. Okay. And then they also say such a signal can successfully replace an audio frequency generator when you are trying to tune audio frequency amplifiers or interphones or whatever. I understand the principle. I cannot really come up at this point with a useful use case for this. If somebody can give a suggestion for this, let me know. Then next we have the output. That's this one over here. Yeah, you can get the output of the signal generator. So I guess it's this connection over here. And the point, this is a high impedance output. So the point of this is that you could connect a voltmeter to this, and then your voltmeter becomes, let's say, a vacuum tube voltmeter, because you have the signal generator in between your the source that you're measuring and your actual voltmeter. So if you had a normal voltmeter already laying around, you can use this output to upgrade it, let's say, to a vacuum tube voltmeter, which is quite nice. And then they say you can also connect an oscilloscope easily to these connections. Okay, so then next we have the two dials over here. This is continuous. This is not. It's in steps. So this is the attenuator on the input, and it's also very simple. If you look here at the schematic, see, it's this guy over here. It just selects a series of resistors that you put in series with the input signal, so you can attenuate your input signal. This is a sensitivity dial, and that one is here at the output, between the input of the Magic Eye and the outputs of your amplifier, so that you can use to change the reading on the Magic Eye, and then you can use both together to compare different signal strengths. And they go into detail here, and they give an example on how you can use these two dials to calculate the gain of a stage. So you can measure the signal strength on the grid of a tube, on the grid on the input of a stage in your amplifier or in your radio, and then you can measure it also on the output of the stage. Make sure that you have the same magic eye reading on both. You can adapt sensitivity and the attenuator to get the same reading on your magic eye. And then using these two values here, you can calculate the gain of the stage. Quite interesting. And then the only thing we have left still is the fuse here, and that should be a slow blow 1 amp fuse. Yeah, for 220 volts is a slow blow 1 amp fuse. And I noticed that it has already been opened in the past, so let's see what is in there. Difficult. It's not blown. It says bus AGC2. Is it a 2 amp fuse? I have no clue. I think it's a 2 amp fuse. So let's replace that with an 1 amp slow blow. Let's see what we get here. Lucky that I repair pinball machines as well, because these types of fuses, they are not really common here in Europe. We normally have the smaller fuses, but in pinball machines you do have these longer ones, so I do have them available in my stock. Ooh, the 1 amps, they are don't have a lot anymore. Yeah, this is a 1 amp slow blow. Yes. I don't know if it has to be that deep, but whatever. Okay, so first thing we're gonna do is try to open it up. I'm not gonna power it on just yet. I'm first gonna inspect what's inside. Now, there is really nothing on the back except for the voltage regulator. No screws on the bottom either. On the top you only have the screws for the hinge, so it has to go via the front, I guess. It's not in the manual how you should open it up, and there are a lot of screws here. These 4 screws, I think they hold like the speaker in place, and these ones, they all hold these connectors in place, so I'll guess it's just these 4 screws in the corners. So let's see. Okay, that opens up quite easily. Ah, there it is. Okay, let's have a look at the back. Okay, what do we have here? Obviously our transformer, the speaker, the magic eye behind the speaker here. That's really quite funny setup. Here we have the EF86. So that's the first stage after the input. This is our selector switch with all the the attenuator with all the resistors, the neon bulb. Here we have the EZ80 for the rectification. This is the ECL82, and that guy over there, the small one, that's the ECC82. Oh, that should be the ECC82. It's not. It's a 6J6. Okay. So I don't know if that has been replaced. Could be. Here we have the output transformer, I guess. On the bottom, that actually doesn't look too bad. Not a lot of components. We have a couple of electrolytics here that we'll need to check. And we'll also have to check if these guys over here are paper or not. I suspect that they are. Here is another electrolytic, there's another electrolytic. This is probably also a paper cap. So even if we would have to do a full recap, then yeah, still it's not a lot of work. It's like 1, 2, 3, 4, 5, 6, 7, 8 caps maximum. The rest are resistors. This one has been have been cooking quite a bit. And at first sight, I don't see any repairs. I don't think somebody has messed with this, which is quite nice. Maybe they did change the ECC82 into a 6J6. And obviously the fuse was also replaced at some point, but for the rest, I don't see a lot of messing about. That's really nice. Okay, and here we, of course, we also have the filter can. So that one will also need to be checked. So first I want to do these basic checks like the transformers, the tubes and the filter can. See that nothing is shorted, and then we can try to power it up. Okay, so I've been thinking a bit, and the 6J6, which is sitting over here, well, that doesn't match with the schematic. So it does say here an ECC82, and an ECC82 is not, oh, it's a bit too bright. An ECC82 is not a replacement for a 6J6. So there wasn't an ECC82 in here originally. An ECC82 is a 9-pin tube, no-vol, and this is a 7-pin. See, it's a smaller tube. So either there were different versions of this signal tracer, which used different tubes here, because see on the schematic, we don't have this tube marked, right? We just have here in the list of tubes the ECC82, but on the schematic itself it's not marked. I assume that this was originally with an ECC91, which is an equivalent for a 6J6, or this originally had an ECC82 and was then replaced at some point by a 6J6, but that would mean that this socket would have been changed, and this socket would not have been original, but I don't think that's the case. See, this is the socket, and honestly, that all looks original, or let's say factory. The bolts on here are the same that have been used. The hole is, yeah, it's a smaller hole than these guys over here, so that looks original. And I don't think the 6J6 was in there originally. It might have been like an ECC92 or something, but at least that's different from what is listed here on the schematic. Okay, it's tube testing time. Let's start with the EF86. That's a Telefunken one. Six, two, 3, 4, 150 volts on the screen, 250 volts on the plate. So, and we should measure 3 milliamps here. It's actually quite a bit higher. See, I'm now on a scale of 10 milliamps, so the top scale, and I am above 4, so that's really good. And the mutual conductance should be 1.85, and that's 5.5 minus 3, but that tube is fine. So next up is an ECL82. That's the power amplifier and preamp. It has two electrodes inside, so the C stands for a triode and the L is a pentode. So let's start with the triode. And here we should measure 4 milliamps of plate current. There it comes. 2 milliamps. 3 milliamps. And it's still climbing slowly. 3.2 milliamps. That's fine. That's more than 75% of the tube of the original rating, so that's fine. Let's give it a couple more seconds and let it stabilize. Yeah, 3.2, I think that's more or less it. Mutual conductance should be 2, so we have almost 5, let's say 4.9 minus 2, that's almost 3 even. So mutual conductance is really good. So the triode section here of this tube is perfectly fine. Now the pentode. And here we should measure 65 milliamp. Wow. So my top scale is now 100 milliamp, so we should get over there somewhere. Whoa, nice. 70 milliamp, 75 milliamps, almost 80 milliamps. Wow. That's a really strong one. Yeah, 80 milliamps. Ha, great. The mutual conductance should be 8 milliamp per volt. So now I have to change this one to 1 volt below and 1 volt above. That's not gonna be that easy because I have times 5 multiplication here on the grid bias voltage. So I should only do this, like one small mark here is now half a volt. So I don't have a lot of wiggle room here. So it's now 82 milliamps. If I increase this like that, that is now 77. Yeah, 77 milliamps. And if I go over there, I get 89 milliamps. So that's 12 milliamps per volt. Of course, yeah, this is not gonna be that accurate because the scale here is not easy to work with. And they say here 8 milliamps per volt, so that's more than good enough. Yeah, this tube is still very, very good. Okay, next up is the EZ80. It's also Telefunken. That's the full wave rectifier, so this has 2 diodes inside. So, okay, just as I expected, in test equipment, often all the tubes are still really good because test equipment is not used as extensively, obviously, as a radio or any audio gear. It's not running constantly, it's only being used, in very short, for very short time periods compared to a radio, which is playing for hundreds or thousands of hours. So most of the time the tubes in test equipment, if they are working, then they are still really strong, and that's also what we see here. These tubes, they are perfectly fine. Now, just for fun and giggles, I also removed the EM80. That's also a Telefunken one. So all the tubes except the 6J6 are Telefunken, so maybe the 6J6 has been replaced at some point. Now, this will be difficult to show because, let me see if I can get the camera in the back there. See, it is glowing really well, and see, it is. You can clearly see the magic eye glowing, and the thing is the tube tester is only testing it at 100 volts on the plate and on the screen. So yeah, and you can even see the magic eye glowing at this point. And if I change the grid bias here, it should go open and closed. Let's see. See, yeah, that's closing. This is opening all the way. See, so the magic eye is working perfectly fine. So see, the Funke tube tester tests the tube with only 30 volts on the plate, but with 150 volts on the screen. Whereas my tube tester only suggests 100 volts on the screen, and both on the screen and on the plate. And the Funke tube card, the Funke tube tester card references as a typical operating condition 250 volts on both the plate and the screen. So let's now put the screen here on 250, the plate also on 250, and then let's hit it, and then you'll see that normally the tube should light up much brighter. See, there it is, and it's really working very well, very nicely, and very bright. So yeah, the EM80 is also working perfectly fine. So all the tubes are good. So now we can continue with checking the rest of the components of the signal tracer. Okay, so while checking the power supply here a bit, I did find a couple of weird things. So I've been checking the power transformer. I can't find any shorts at first sight, so it seems that the power transformer is fine. What is funny though is that here you have the voltage selector. It goes up to 245 volts, but the tap for 245 volts is not connected. So the power transformer in there doesn't have a tap for 245 volts. So the maximum is still 250, even though you can set it here on 245, it just won't work. And in that sense, the schematic is correct, because see, you have here a, damn, it's way too bright again. See, you have here a 3 taps, 110, 130 and 220, so there is no 245, so that seems to be correct. Now, what isn't correct though is the way that the EZ80 is wired. Well, correct, it's not according to the schematic, because see, here we have, so the EZ80 is basically 2 diodes with a common cathode in the tube. So both anodes are connected to the secondary of the transformer, which is a center tapped and connected to chassis. So you have both diodes here, so you should have full wave rectification in this way, right? Now here, if I am correct, only one of the 2 diodes is being used here. That might also explain why we saw a bit of an asymmetry between 2 diodes on the tube tester, because one of the 2 diodes is simply never used. On an EZ80, you have the 2 anodes are connected to pin 7 and pin 1. And here this is pin 1. Let me bring it in a bit closer. See, so there you have pin 1, that's going to the transformer. So I guess this is one side of the secondary of the transformer. But pin 7, 1, 2, 3, 4, 5, 6, 7, see, pin 7 is unconnected. So that diode isn't used, so we only have a halfway rectification here. So that's the first major change I'm noticing here in the entire power supply section. The second change is that these capacitors that are mentioned here and the values, they are not correct either. So the filter cans, which I would guess are then here C9 and C10, they are here mentioned as 2 times 50 microfarad. Well, they're not. This is a can, the can says 16 microfarad, so 2 times 16 microfarad, 450 volts. So these values are quite different. So what we can do is we can see how they actually measure. So this is actually not too bad. The ESR seems fine, capacitance is slightly high. bit more than 10% high, so they are on the edge of what I consider acceptable. Most of the time I consider 10% as acceptable. These are slightly high. Let's check this guy over here. That's a 10 microfarad at 15 volts. Whoa. Really? Whoa, that's really bad. This one I can't read. That 50? That 50 microfarad? Wow, 80 instead of 50. ESR of 1.7. That's also not great. But the thing is, I can't seem to find these on the schematic. This is on the EF86. Yeah, there is indeed a gap on there between ground and the cathodes. Yeah, but see, that's C2. That's the cathode bypass cap. But C3 says that's removed, so not in circuit. So I do think that these values are not correct for the model that I have here. So that's this one. Then this guy is between, this is on the ECL82. So that, I guess it's C6. C6 is 20 microfarad, and here I guess it's 50 microfarad. So see, all these values here, they are all different. So these guys over here, they are supposed to be 8 microfarad. So see what, let's see what we get here. 9.2, and this one 9.1 instead of 8. It will still work, but it can be better, I guess. And so it's one of those is this guy over here, C11, C11 8 microfarad, but the other one, I don't find any other electrolytics. See, we have 1, 2, 3, 4, 5, 6 electrolytics here, and here on the schematic we only have 1, 2, 3, 4, 5. I think I'll need to look a bit online if I find a better schematic, or I'll need to adapt this one. In any case, if you're ever working on a similar radio, on a similar signal tracer, then just as a reference, this one is a 10 microfarad at 15 volts. This is a 50 microfarad at 15 volts. These guys are 8 microfarad at what is it? 350 volts. And this can has 2 times 16 microfarad at 450 volts. So I believe that the caps will still work, but these two should definitely be replaced. These, I will probably also replace them. And the paper ones, I think these are paper, they will also have to go. Yeah, in the meantime it started raining here pretty badly, so if you hear some noise in the background, yeah, that's just the rain. Quick test of the speaker. I hooked up the signal generator to the primary of the output transformer, and I'm putting in a signal. Let's see if the output transformer and the speaker are still fine. Yeah, I can hear something. Let me up the amplitude a bit. Okay, so the output transformer is fine, the speaker is fine, that's also good. Now these capacitors over here, let me show you how they measure, because they measure still quite okay. See this guy over there, that's 0.1 microfarad, and that one is, see, exactly 0.1. 100 nanofarad exactly. This one, same thing, also 0.1 microfarad. See, also measuring perfectly fine. This one, unfortunately, I cannot read it because the print is at the back. I don't know what it should be, but it's measuring 20 nanofarad. And what should it be? It's a 400 volt. .022, so it should be 22 nanofarads, and it's measuring 21, almost 21, so that one is also still fine. So, and these guys over here, they are also, see, they are 10 nanofarad, or they should be 10, 9, and this one 10. See, so these caps, they seem fine, honestly. If somebody knows what they are, see, they have a marking on them. See, so they have a marking, Neofar, .1 microfarad, 10%, 400 volt. So obviously, I don't know if they are leaky, but capacitance is still okay. If somebody knows whether these are paper or not, let me know. First measurement suggests that they don't need to be changed, but yeah, let me know if you know more about these types of capacitors. And this guy over there, that's a different type. That's a .05 microfarad. And that one, where is it connected? Over there. Yeah, measuring this in circuit is not perfect, but at least we can get an indication. Okay, .05, so that should measure 50 nanofarad. But I'm measuring like 85 or something. It's 95. Okay, I need to take this one out of circuit and check it. That might be a paper cap that needs to be replaced. It's an RFT 905 VEB .05 microfarad at 500 volts DC. So that one, I think that's paper and that will need to go. Okay, so I believe that there are only a couple of electrolytics that still need to be swapped. There is maybe one paper capacitor that needs to be swapped, the last one that we checked, and that's this guy over here on the grid for the Magic Eye. See this C8. Now all the tubes are fine, and I think both transformers are also fine. So I'm going to plug it in and see what it does. Now, related to the electrolytics, there are basically two ways to go. I could replace the majority of them, or I could bring up slowly the signal tracer and let them reform. I'm not a fan of reforming capacitors anyway, so I'm not gonna go that route. It's also, it has a tube rectifier, so bringing it up slowly is also not that convenient. Anyway, the capacitors are, let's say, 60 years old, so they will have to be changed anyway. So I hooked up the signal tracer to the dim bulb tester and to my isolation transformer. I'm going to power it up very slowly with a very restrictive bulb in between. And here I have the B plus connected. So this is, I have this connected here on the plate of the ECL82. So right over here to pin 6 of the ECL82. So we should get there something above 250 volts, because I don't have any markings here of what the B plus should be. But as you see over here, we should have 250 volts, and then we go here through a resistor of, if this is correct, like 1K, and then we go through the output transformer, so it should be above 250 volts a bit, because yeah, the voltage is coming from here, goes first to the ECL82, then to the dropping resistor, and then it goes then it becomes 250 volts more or less. So we should be slightly above 250, but yeah, in the beginning we should be well below. So let's start with that first. Let's see. So I'm just going to start with a 15 watt bulb. That's a really high restriction. Just to see if nothing shorts and nothing blows up. Okay, so let's turn on the dim bulb tester. And let's turn on the signal tracer. Okay, the bulb is glowing really bright, but it's, yeah, a 15 watt bulb. It's drawing 2 watts at 40 volts, so that's not nearly enough. So let's go to my next bulb, and that's a 25 watt. Okay, let's go to a 25 watt bulb. Okay, that's also glowing brightly. 80 volts, 90 volts, 97 volts, 100 volts. It's coming up slowly. Let's give it also the 120 volts. Gonna leave it at this for a second. See if we get something. The bulb is dimming, so that means we don't have a short. Capacitors are charging, and we have B plus here. B plus is growing. 70, 80 volts. I see the filaments of the tubes glowing. 100 volts. It's stabilizing at 90 volts. I hear something. Ha 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 ha! Okay. Okay, there is probably this switch needs to be cleaned. See? It's now running at 110 volts. Let's just give it the 15 watt bulb also in there. So now I have 40 watts. Oh, it's 140 volts. I can hear my cell phone in the signal tracer. See, and the magic eye is glowing. Seems like it's working. This switch needs to be cleaned, man. Alright. Maybe we can go to, I'm not, what did I say, 40 watts? What is my next bulb? It's 40 watts, so if I do the 25 and the 40 together, that's 65 watts. And now we are at 190 volts going in, 140 volts B+, that's really low. That's really low. Jesus. This is loud. But it's working. See, and the sensitivity is also... The point of the sensitivity is to adjust the deflection of the magic eye. See? So that's working as it should. We're at 190 volts going in, but only at a deep B plus of 150. That's really low. Okay, now 200 volts going in, B plus is 160. The capacitor is not heating up. Yeah, what else can we do? We can maybe try to go to 220. Let me swap the 40 watt bulb for a 60 watt bulb. Now it's 222 going in, 220, and I have a B plus of 173. And am I wrong here? But I think that should be higher. It's here on the plate of the ECL 82. Yeah, okay. let's not jinx our... there is only one thing that I would like to still try. What happens if we use here the RC circuit, which is the circuit used to test continuity. I have the B plus disconnected now, well, the voltage. So let's see, will this light up or not? Yeah, see? So this is indeed continuity tester, see? And let's just take a resistor here. See? So that neon bulb is indeed working. And they say that you should also be able to use this to test leakage of a capacitor. So I have here a 0.1 microfarad 650 volt capacitor. See? Nothing. Over there, on the neon bulb. Maybe I can now take an old cap, of which I'm sure that it's leaky. See, this is an old capacitor that comes out of a radio I restored. I don't know anymore which one. It's a .047. Let's see what we get with this one. Huh. I don't see the neon bulb, so... Nope. Let's take another one. No. Honestly, I don't believe that these caps are not leaky. Ah, yeah, see. Let me close down, turn out the light. See? This one is lighting up. So, yeah, that one is clearly bad. So it does work. Okay, let's turn it off before something blows up here. So, what I'm going to do now is obviously clean the thing a bit. Change some of the electrolytics, maybe all of them, probably all of them, and change that one other capacitor or check if it is bad or not, and clean the switches over here. This potentiometer probably also needs to be cleaned. This switch definitely needs to be cleaned, and also checking the resistors, see if they are still in spec. So, and I'm also going to try and find a better schematic if that exists online. Not sure yet. And then I'll come back to you when I'm finished with that. And then the next step, what we will do in the next part, is creating this probe, this demodulation probe. I have an old probe from an old oscilloscope still laying around that I don't use anymore. And I'm just going to convert that to a demodulating probe. I have a germanium diode and I have a capacitor and a resistor to put in there, so that's not going to be a problem. But that'll be for the next video. So I hope you enjoyed this so far. I certainly have. It's a really cool piece of equipment, really, yeah, vintage test equipment. I always love vintage test equipment, but this one is pretty cool. Also the design with the speaker here in the middle and the magic eye in the middle of the speaker, it's quite original, and it looks quite great, and I think if it's cleaned up it's gonna fit nicely on my shelf. So enough waffle for today. If you are still watching, I would like to thank you for watching, and if you like what I'm doing, if you want to follow along the repair of this signal tracer, then subscribe to the channel and like the video. That always helps. And then I'll see you in the next video. Take care. Bye bye.